Section 9.5 Equivalence Relations. Definition. A relation on a set A is called an equivalence relation if it is reflexive, symmetric, and transitive. Second definition, two elements A and B that are related by an equivalence relation are called equivalent. The notation A equivalent to B is often used to denote that A and B are equivalent elements with respect to a particular relation. Example: suppose that R is the relation on the set of strings of English letters such that A is related to B if and only if the length of A is equal to the length of B, where the length of X is the length of the string X, that is the number of letters in the string. If R is R an equivalence relation. Solution: show that all of the properties of an equivalence relation hold. Reflexivity: because the length of A is equal to the length of A, it follows that A is in relation with itself for any string K. Symmetry: suppose that A is in relation with B. Since the length of A is equal to the length of B, the length of B is also equal to the length of A, which means that B is in relation with A. Transitivity: suppose that A is in relation with B and B is in relation with C. Hence, the length of A is equal to the length of B and the length of B is equal to the length of C. Therefore, the length of A is equal to the length of C. The length of A is equal to the length of C, which means that A is in relation with C. Example: let M be an integer bigger than 1. Show that the relation R, consisting of all pairs AB, such that A is in relation with B mod M, is an equivalence relation on the set of integers. Solution: recall that A is in relation, A is equivalent to B mod M if and only if N divides the difference A minus B. Reflexivity: A is congruent to A mod M, since A minus A is 0, and 0 is divisible by M, since 0 can be written as 0 times M. Symmetry: suppose that A is congruent to B mod M, then A minus B is divisible by M. So, A minus B is equal to K times M, where K is some integer. It follows that B minus A is equal to negative K times M, and of course negative K is an integer. This means that M divides B minus A, and therefore B is congruent to A mod M. Transitivity: suppose that A is congruent to B mod M and B is congruent to C mod M, then M divides a minus b, and m divides b minus c. So they are integers k and l such that a minus b is km and b minus c is lm. When we add these two equalities, we get a minus c equals this sum, which is km plus lm, which is k plus l times m. K plus l is an integer. This means that m divides a minus c, and therefore a is congruent to c mod m. Show that the divides relation on the set of all positive integers is not an equivalence relation. Solution: we'll see that the properties reflexivity and transitivity do hold, but the relation is not symmetric. Hence, divides it is not an equivalence relation. Reflexivity: A divides A for all A in the set. This is obvious because A can be written as 1 times A. So A divides A. The relation is not symmetric because, for example, 2 divides 4, but 4 doesn't divide 2. Transitivity: suppose that A divides B and B divides C. Then there are positive integers k and l such that B is ak and C is bl. Hence C is equal to, replace here B with ak. So C is akl. So A divides C. Therefore, the relation is transitive. Equivalence classes. Definition 3. Let R be an equivalence relation on a set A. The set of all elements that are related to an element A of A is called the equivalence class of A. The equivalence class of A with respect to the relation R is denoted this way: A in brackets with index R. When only one relation is under consideration, we can write only A in brackets to denote this equivalence class. Note that this definition means that the class of A is the set of all elements S such that the pair AS is in the relation R. If B is an element of the class of A, then B is called a representative of this class. Any element of a class can be used as a representative of the class. The equivalence classes of the relation congruence mod M are called congruence classes mod M. The congruence class of an integer A mod M is denoted this way, and it consists of all these integers: A minus m, A plus m, A minus 2m, A plus 2m, and it continues indefinitely in both ways. For example, if m is 4, the class mod 4 of 0 consists of all multiples of 4. The class of 1, mod 4, consists of all these numbers that have remainder 1 when divided by 4. The class of 2 consists of all integers which have remainder of 2 when divided by 4. And this is the class of 3 mod 4. Theorem 1. Let R be an equivalence relation on a set A. This statement for elements A and B of R are equivalent. First, A is in relation R with B. Second, the class of A is equal to the class of B. Third, the intersection of the class of A and the class of B is empty. The proof consists of these implications. 1 implies 2, 2 implies 3, and 3 implies 1. How we show that 1 implies 2? Assume that A is in relation with B, and to show that 2 holds. A is in relation with B, this is given. We want to show that the class of A is equal to the class of B. These are sets, so we prove 2 opposite inclusions to prove that these 2 sets are equal. Select an element C of the class of A. This means that A are C because A are B is given. This means that B are A because R is transitive. Because the relation is symmetric, we have from A R B, we have B R A, and because R is transitive, from B R A and A R C, we have B R C. This means that C is in the class of B. That is, any element C of the class of A belongs to the class of B, therefore A is a subset of B. Similarly, we can prove the other inclusion, and from both opposite inclusions we conclude that these 2 classes are equal. How we prove that 2 implies 3? 2 means that the class of A is equal to the class of B. What is then the intersection? It is the class of A. But the class of A contains the element A, so it is not empty, hence the intersection is not empty. And this is just the statement 3. The intersection is not empty. 3 implies 1. How we prove this? Given 3, we are given that the intersection of these 2 classes is not empty. This means that there is an element C in that not empty intersection. This C belongs to A, so it must be in relation with A, and this C must be in relation with B because it is in the class of B. Therefore, C are B, because R is symmetric, and by transitivity from this ARC and this CRB, we conclude that ARB. But this is just property 1. Definition. Partition of a set. A partition of a set S is a collection of disjoint non-empty subset of S that have S as their union. In other words, the collection of subsets A sub I, where I belongs to some index set capital I, forms a partition of S if and only if these three requirements are met. Each A sub I is not empty. Two different indexes produce disjoint subsets A sub I and A sub j. So the intersection is empty. And the union of all different subsets is equal to the whole set S. Theorem 2. Let R be an equivalence relation on set S, then the equivalence classes of R form a partition of S. Conversely, given a partition A sub I for I in the index set I of the set S, there is an equivalence relation R that has the sets A sub I for I in the index set I as its equivalence classes. Proof. We have already shown the first part of the theorem. The equivalence classes of an equivalence relation form a partition of the set. For the second part, assume that A sub I, this collection of subsets, is a partition of S. Let R be the equivalence relation consisting of all pairs X, Y, where X and Y belong to the same subset A sub I of the partition. We must show that R satisfies the properties of equivalence relation: reflexivity, symmetry, and transitivity. The first property: for every element A of S, the pair AA belongs to R because A is an element of the same subset as itself. The subsets are disjoint, so A belongs to only one subset. Symmetry. If AB is in R, then BA is in the same subset of the partition. So the two elements belong to the same subset, so both pairs, AB and BA, by definition belong to R. Transitivity. If AB is in R and BC is in R, these two pairs, this means that the elements AB are in the same subset of the partition and B and C are in the same subset. But the subsets are disjoint, so B must belong to both subsets and they must be equal, identical. Therefore, A and C belong to the same subset of the partition, and this means that A, C, this pair is in the relation.